Next, I will explain a method to find the greatest common divisor of any pair of integers, and that is called the Euclidean algorithm. So here's the theorem. Okay, let A, B, D be non-zero integers. Non-zero integers. And also assume that D is a positive common divisor of A and B. Okay, if there exists integers x and y such that ax plus by is equal to d, then d is the greatest common divisor of A and B. So let's prove this one. So by the way, what is the definition of the greatest common divisor? It is a common divisor uh, that is divisible by any common divisors, right? So let C be any common divisor of A and B. Okay, what we want to show is C divides D. Okay, we want to show this. So, since C is a common divisor, uh, we have A equal to C times A prime and B equal to C times B primes. And A prime and B prime are some integers. Okay, so there exists A prime and B prime such that these equations hold. Okay, then since we are assuming that this equation holds, we substitute A and B into that equation. So ax plus by is equal to ca prime times x plus cb prime times y. Factorizing by c, we have this b prime y, but this is equal to d. This means c is a divisor of d. Therefore, c divides d. So since c is any common divisor of a and b, this means d, and also by assumption d is of course a common divisor. This means d is the greatest common divisor of a and b. And we are done. Let's see an example. Okay, so consider two integers, 291 and 388. And you can validate this equation. 291 times 15 plus 388 times negative 11 is equal to 97. Okay, and you should see that, also check that 97 is a common divisor of these two numbers. Okay, then according to the theorem, this 97 is the greatest common divisor. And this you can also check by finding all the common divisors of these two numbers. And one question you should ask is, how do you find these two numbers, 15 and negative 11, to find this equation? And that will be a central subject in the following discussion. Next, consider the problem of finding the greatest common divisor of these two numbers, 4,947 and 1,552. Okay, so how do we find the greatest common divisor of these two numbers? And actually, what we are going to do now is an application of the Euclidean algorithm, which we will explain later. Anyway, first we apply the division algorithm. So 4947. So if we apply the division algorithm, this is 1552 times 3 plus 291. Okay. Now, next we divide this number by the remainder. Okay. And apply again the division algorithm. 1552 is equal to 291 times 5 plus 97. Now, we divide this number 291 by this remainder 97, and that would be 97 times 3, and in this case the remainder is 0. And now we claim that 97 is the greatest common divisor. Okay. And first, we should check that this is a divisor. Okay, the greatest common divisor is a divisor that is the greatest among all divisors, right? So first thing we need to check is that it is a divisor. So we need to show that 97 divides both 4,997 and 97 divides 1,552, and this you can check. And so please calculate this and confirm that this 97 is a divisor. Okay, and then let's see. From this equation, we have 97 is equal to, moving this one to the left, we have 1552 minus 291 times 5. Okay, and now this 291 is found as the remainder in the first equation. So moving everything to the left hand side, we can get rid of 291 from this equation. Okay, so that is 4,947 minus this one, 1,552 times 3, right? And by expanding this, we have, wait a minute, times 5. Okay, so this number is replaced with this expression. So times 5 is still here. So by calculating this, expanding this, we have 4,947 times negative sign is here, so negative 5, and plus we have this number 552 times 1 and 5, so that's 6. Wait a minute. So we have 3 here. So 3 times 5 plus 1, so that's 16. So this is the form we found in the theorem. So just like this. So in this case, D is 97 and A is 4,947 and B is 1,552 and X is -5, yeah, and Y is 16. Therefore, from the theorem, we can confirm that 97 is the greatest common divisor of these two numbers. Now extend that result to the general case. Now so that is the problem of finding the greatest common divisor of any two integers. Okay, fine. For simplicity, we assume both are positive. Okay, and also without losing generality, we can assume that A is greater than B. Okay, if opposite is true, then we just swap the roles of A and B, and we can apply the same result. And for convenience, we write A0 as A and A1 is B. Okay. Now we apply the division algorithm repeatedly. First, divide A0 by A1. Quotient is Q1 and the remainder is A2. And of course, A2 is non-negative and less than A1. Okay. And again, we apply the division algorithm. In this case, we divide A1 by A2. The quotient is Q2 and the remainder is A3. And A3 is less than A2. And we do this over and over. Until the remainder becomes 0. Since the remainder gets smaller and smaller every time we apply the division algorithm, eventually it becomes 0. So that step, let's label that step as n. So at the end we have something like this, an qn. So before that step, so at this step the remainder is 0, and previous step will be an minus 2 equals to an minus 1 qn minus 1 plus an, and of course an is less than an minus 1, and the previous to that step is n minus 3 minus 2 qn minus 2 plus an minus 1 2. Okay. Now, in conclusion, this an will be the greatest common divisor of A and B. But we'll explain how that is the case. Okay. First of all, look at the last equation. From this, we can clearly see that an divides an minus 1. Okay. And if we substitute this an minus 1 into here, we can see that an minus 2 is an qn times qn minus 1 plus an. So we factorize by an. So this means an divides an minus 2. Next, look at this equation. Since an divides both an minus 2 and an minus 1, that means an also divides an minus 3. So we can continue this up to this equation, this and this equation. So after all, we can show that an divides a1 and an divides a0. So this means an found here is a common divisor of a and b. Next, if we can show that we can find this equation. If we can find some integers x and y such that this equation holds, then from the previous theorem we can claim that an is indeed the greatest common divisor of a and b, and that is a0 and a1. So how do we do that? To do that, look at this equation first. This one. So moving this term to the left hand side and swapping sides, we have an equals to an minus 2 minus an minus 1 times qn minus 1. And let's see, from this equation, and we have an minus 1 is equal to an minus 3 minus n minus 2 times qn minus 2. Then we substitute an minus 1 here to here. So we have an minus 2 minus an minus 3 minus an minus 2 times a qn minus 2 times qn minus 1. Expanding this, we have an minus 3 times qn minus 1 plus an minus 2 a qn minus 2 times qn minus 1, but we have an minus 2 here and here. So factorizing this, we have an minus 2 1 plus qn minus 2 qn minus 1 minus an minus 3 times qn minus 1. So here we just got rid of an minus 1 from the equation. And we can continue this repeatedly. Then next we get rid of an minus 2 by using equation that is just before this one. And we can repeatedly apply the same procedure, and after all we will have something like this. So this x and y are some complicated expression involving all these terms, something like this. So by the theorem we have proved before, an is indeed the greatest common divisor of a0 and a1, that is a and b. And this way of finding the greatest common divisor is called the Euclidean algorithm. And if you can write programs, you should implement this algorithm. This can be implemented by a recursive procedure.